Today we're going to continue our discussion of acids and bases, but today we're going to focus more on bases. So let's start with strong bases. We know that the stronger the base, the more willing it is to accept hydrogen ions. And typically we use water as the standard acid for a base. And off to the right we can see a strong base, sodium hydroxide, and it is dissociating in solution to produce hydroxide ions and sodium ions. Now, for strong bases like sodium hydroxide, practically all of the units are dissociated into hydroxide ions and sodium ions. So we would also consider strong bases to be strong electrolytes. Now, what if we have a base with multiple hydroxide ions? So for instance, magnesium hydroxide has 2 hydroxide ions associated with the magnesium ion. These will completely dissociate in one step. So we're not going to lose one hydroxide ion at a time. We're going to see that both hydroxide ions completely dissociate from the magnesium ion. And this is in contrast to a diprotic acid, which has 2 hydrogens attached. So for instance, carbonic acid is not going to lose both hydrogens at once. It's going to lose one hydrogen at a time. So first it loses that first hydrogen, and then it loses the second hydrogen. And both of these processes are reversible, although in the first step, the products are pretty highly favored. Okay, now what about weak bases? In weak bases, only a small fraction of molecules will accept hydrogen ions. So we would consider weak bases to be weak electrolytes. What this means is that most of the weak base molecules do not take hydrogen ions from water. And in fact, we see much less than 1% ionization. So the ammonia molecule, for instance, will produce ammonium ions and hydroxide ions in solution, but only to a certain extent, so we still have some ammonia molecules left in solution. What that means is that the concentration of hydroxide ions will be much, much less than the concentration of the weak base. So if we want to find the pH of a weak base solution, we're going to use a very similar method that we used previously to find the pH of a weak acid. But before we go over an example where we find the pH of a weak base, I want to go over some other concepts first. So previously, we've looked at acid ionization constants, Ka, but bases also have an ionization constant, Kb. And base strength is measured by the size of that equilibrium constant when it reacts with water. So if we write out kind of a generic equation here between a base and water, we would find that the products are hydroxide ions and the conjugate acid of the base, which is BH+ in this example. Now, the equilibrium constant for this reaction is called the base ionization constant, Kb. And the larger the value of Kb, the stronger the base. And this is very similar to Ka. So the larger the value of Ka, the stronger the acid. So down below, we can see the expression for Kb is equal to the concentration of the conjugate acid times the concentration of hydroxide ions divided by the concentration of the base. So if we have a really large value of Kb, that means that we have a lot of product that's forming. And if we have a lot of product, that means that the base is really strong. It very easily dissociates in solution to produce products. Now, if you have a smaller value of Kb, that means you have a weaker base. And in your textbook, there's a list of some common weak bases. So at the very top, we have the carbonate ion. And as we go down the list, you'll notice that the Kb values are getting smaller and smaller. So that means these bases are getting weaker and weaker. So at the very bottom of the table, we have something called aniline. And this is a really, really weak base. You might also notice that many of these bases have a nitrogen atom. And I had mentioned previously that common weak bases tend to have a nitrogen atom within them. So if we look at a couple of examples here, we have ammonia on the left, which we've seen examples of before, that's NH3. And then methylamine is CH3NH2. And pyridine on the very far right is C5H5N. So what all of these different weak bases have in common is the nitrogen atom with a lone pair of electrons. And that lone pair of electrons can grab onto a hydrogen ion from an acid. And then it can become a conjugate acid. Now, if we look at our generic reaction of an acid with water again, we know that the products are the hydronium ion and the conjugate base, A-. So A- can also be called an anion because it is negatively charged. So remember that anions are negatively charged and cations are positively charged. Now, every anion can be thought of as the conjugate base of an acid. Therefore, every anion can potentially be a base. So down below we have essentially the reverse reaction where the A- is reacting with water to produce a conjugate acid and a base. So we've got our base, our acid, our conjugate acid, and then the conjugate base. So knowing that an anion can act as a base, potentially, we can also start to think about the relative strengths of those anions or those bases. And in general, the stronger the acid, the weaker the conjugate base. So let's look at a couple of examples of conjugate bases. So for instance, let's say we have a reaction of water and hydrochloric acid. So we have a strong acid, hydrochloric acid, and when it reacts with water, it completely ionizes. So we end up with hydronium ions and chloride ions. Now, we said that the stronger the acid, the weaker the conjugate base. So in this instance, the chloride ion is the conjugate base. And we can see that we don't have a reverse reaction here, which means that the chloride ion is not going to act as a base, and reform the hydrochloric acid. So no reverse reaction. So down below we have that potential reverse reaction. So if we put chloride ions in water, we would not see the formation of hydrochloric acid and hydroxide ions. So that forward reaction does not occur, only the reverse reaction. So an anion that is the conjugate base of a strong acid is considered pH neutral. This is not, oh, my pen isn't working, not a base. But it also isn't an acid either. It doesn't have a hydrogen associated with it, so it can't act as an acid either. Now, what if we have a weak acid, such as hydrofluoric acid? We've seen before that hydrofluoric acid reacts with water to produce hydronium ions and fluoride ions. And those fluoride ions can react with an acid to reproduce hydrofluoric acid. So that means that the fluoride ion can act as a base. So that means the conjugate base of a weak acid is basic. So if we performed the reverse reaction where fluoride is reacting with water, we would end up with hydrofluoric acid and hydroxide ions. So in your textbook, there's this nice handy chart of acids and their conjugate bases, or vice versa. And at the very top, we have a strong acid, hydrochloric acid, and its conjugate base, the chloride ion. And we can see that there are other examples of strong acids and their conjugate bases. And the conjugate bases of these strong acids are considered neutral. And then as we move down the chart, we get into some weak acids and weak bases. So we looked at the example of hydrofluoric acid and its conjugate base, the fluoride ion. And we know that we have a reversible reaction there. So while the hydrofluoric molecule can act as an acid, its conjugate base, the fluoride ion, can act as a base. And then when we get down to the bottom of the chart here, we have a really strong base, the oxygen anion. And then its conjugate acid is the hydroxide ion. And we know that the hydroxide ion does not act as an acid. It prefers to act as a base. So that means that the conjugate acid of a strong base is negligible. So it's not going to act as an acid, at least not to a significant extent. Now, one more concept I want to cover is the relationship between the acid ionization constant and the base ionization constant. So how do Ka and Kb relate to each other? Now, many reference books will give tables of only Ka values, and that's because we can find Kb values from those Ka values. So let's talk about why that is. So let's say we have our acid and water reaction, and then our base and water reaction. So again, when an acid reacts with water, we end up with hydronium ions in the conjugate base. And when a base reacts with water, we end up with the hydroxide ion and the conjugate acid. And we can write out the acid ionization constant expression for the first reaction. And then we can also write out the base ionization constant expression for the second reaction. So Ka is equal to the concentration of hydronium ions times the conjugate base concentration divided by the concentration of the acid. And then Kb is equal to the concentration of hydroxide ions times the concentration of acid, the conjugate acid, divided by the concentration of the base. Now, if we want to find the overall reaction here, we can cancel out any acids that appear on the left and right-hand sides of that arrow. And we can also cancel any bases that appear on the left and right-hand sides. So, for example, HA appears in the reactants and the products. So we can cancel that out. And then A- also appears in the reactants and the products, so that also cancels. And what we're left with are two water molecules on the left-hand side of those arrows. And then we are also left with a hydronium ion and a hydroxide ion on the right-hand side of those arrows. So that would be our overall reaction. Now, if we write the expression for that reaction, we would find that it's equal to the concentration of hydronium ions times the concentration of hydroxide ions. Because again, we don't include pure liquids in our equilibrium expressions. However, in chapter 15, we learned that we can also multiply the equilibrium expressions for two equations if we're adding them together. So down below, we're going to multiply Ka times Kb to get the equilibrium constant expression for the overall reaction. So if we multiply those together, we find that certain things cancel again. So A- will cancel because it's in the numerator and the denominator. And HA will also cancel. So again, we're left with the concentration of the hydronium ions multiplied by the concentration of the hydroxide ions. Now, a while ago, at the very beginning of chapter 16, we said that that was equal to something called the ion product constant of water, or Kw. So what this tells us is Ka times Kb is equal to Kw. And Kw, we said, was equal to 1 times 10 to the negative 14th. So we can use this equation to solve for Ka or Kb of an acid and its conjugate base. So as an example, let's say that we have the Ka value for acetic acid, which is C2H3O2. So this is acetic acid. And its Ka value is 1.8 times 10 to the negative 5th. And what if we want to try to find the Kb value of the conjugate base, which is acetate? Oh, sorry. And again, it's really hard to find Kb values in reference tables because we can just use that equation that we just derived in order to solve for Kb. So typically, reference tables will only give you the Ka values. So let's plug in what we know. We know that Ka is equal to 1.8 times 10 to the negative 5th. We don't know what Kb is. And then we know that Kw is 1 times 10 to the negative 14th. So if we rearrange, Kb is equal to 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. So if you want to plug that into your calculator and solve for Kb, you can. You should get a value of 5.6 times 10 to the negative 10th. So that is the Kb value for acetate. Now, one more thing. Remember that previously we said that pH plus POH is equal to 14. We can actually do the same thing here. So what if we take the negative log of everything in our equation oh, sorry. I meant to write Ka times Kb what we end up with here is the negative log of Ka plus the negative log of Kb is equal to the negative log of Kw. And that would be the pKa plus the pKb, which is equal to the negative log of 1 times 10 to the negative 14th, that's Kw, and that is equal to 14. So this is really similar to pH and POH, but this time we're using Kb and Ka values. So you can also use this calculation for certain equation, or this equation for certain calculations. Okay, so let's do a practice problem. And this is worksheet problem 6. And in this problem, amphetamine is a weak base with a pKb of 4.2. Calculate the pH of a solution containing an amphetamine concentration of 225 milligrams per liter. Let me pull out my notes here. So this will be very, very similar to how we solve for the pH of a weak acid, but this time we're solving for the pH of a weak base. So let's start how we always do. We're going to write out the chemical equation for amphetamine in water. So in this case, we have a weak base reacting with water. So that means that our weak base, amphetamine, is going to grab onto a hydrogen ion. So it's going to become C9H13NH+. So initially the base was neutral, and then when it gained that hydrogen ion, it also gained a positive charge. And then our other product will be the hydroxide ion because we've taken away a hydrogen from water. And then these will both be aqueous products. So now that we know the reaction, we can write out an ice table. And as usual, I'm going to separate the reactants from the products. Now, we don't actually know the initial concentration of the base in terms of moles per liter, which is what we use for ice tables typically. So we're going to have to solve for that first. So let's go to the next slide, which is blank, and we're going to figure out what the concentration of amphetamine is in terms of moles per liter. Okay, so we want to go from milligrams per liter to moles per liter. So the denominator is staying exactly the same, so we don't have to change the unit of volume, but we do want to go from milligrams to moles. So that probably means that we need the molar mass of amphetamine. So let's calculate the molar mass. So we have 9 carbons. So we'll multiply the mass of carbon by 9. And then we're going to add the mass of hydrogen times 13. And then finally we have 1 nitrogen, which has a mass of 14. So when we do that calculation, we should get a molar mass of 135.22 grams per mole. Okay, so now we're going to convert 225 milligrams into moles. However, if we want to use that molar mass, we first have to convert milligrams to grams so that our units line up. So let's see, for every 1 gram, there are 1,000 milligrams. And of course, you could also say that there are 10 to the negative 3 grams for every 1 milligram. That will give you the same answer. So now that we have converted from milligrams to grams, we can use the molar mass. And now we should end up with moles per liter. So we're going to take 225 and divide that by 1,000 and then by 135.22. So our concentration in terms of moles per liter will be 0.00166. Okay, so now we can go back and put this value in to our ice table. Okay, so that's our initial concentration in terms of moles per liter. And remember, we do need this in moles per liter because later on we're going to calculate the pH, and that really does depend on molarity. Okay, so we're going to assume that we don't have any of our products, although we do have some hydroxide ions present due to the autoionization of water. So it's small enough that we'll say we have approximately 0. And then everything is in a 1-to-1 ratio, which is going to make our next row really simple. So we're losing some amount of our base, and then we're gaining that amount of each product. So now the equilibrium expressions are 0.00166 minus x for the reactant, and then just x and x for the products. Now, in this instance, we're not going to use the acid ionization constant expression. We're going to use the base ionization constant expression. Great. Now, there's just one problem. We were not given the Kb value. However, we were given the pKb value. So we're going to have to do a little bit of math in order to figure out what that Kb value is. Okay, so let's try to determine what the Kb value is. So this is a calculation that's very similar to our pH calculations from a while ago. So we're going to calculate the Kb value by taking 10 and raising it to the negative pKb. So again, this is really similar to if we wanted to find the concentration of hydronium ions from pH, but this time we're using pKb and Kb. So we'll just plug in 4.2 for the pKb value. And when we plug this into our calculator, we should get a value of 6.3 times 10 to the negative fifth. All right, so that gives us our Kb value. And now we're going to set that equal to the equilibrium expressions for each of our products and our reactant. So that would be equal to x squared over 0.00166 times minus x. Now let's assume that x is small. So we're going to ignore that change in x in the denominator. And then we're going to solve for x, just like we would in our previous examples with acids. But this time, x is going to equal the concentration of hydroxide ions. So when we do this calculation, we're going to multiply 0.00166 by 6.3 times 10 to the negative fifth. And then we're going to take the square root of each side. So we should find that x is equal to 3.23 times 10 to the negative fourth. And remember that we should always check our assumptions. And we want to make sure that our percentage here is 5 or less. So we're going to use our concentration of hydroxide ions at equilibrium, and then divide that by the original concentration of the base, and then multiply by 100. Now, unfortunately, it looks like the percentage is 19. So that is much greater than 5. So unfortunately, we cannot make the assumption that x is small. So that means we have to use the quadratic formula to solve for x. Okay. So now we have to go back and try again. Okay, so let's set up that same expression for Kb. But this time we're not ignoring that change in x. So we're going to multiply 0.00166 minus x by 6.3 times 10 to the negative fifth. and then that is equal to x squared. All right, so we should find that we have 1.05 times 10 to the negative 7th minus 6.3 times 10 to the negative 5th x is equal to x squared. And then we're going to move everything over to one side so that everything is equal to 0, and then we can plug our values in for the quadratic formula. So 0 is equal to x squared plus 6.3 times 10 to the negative 5th x minus 1.05 times 10 to the negative 7th. So our value of a in the quadratic formula is 1, b is 6.3 times 10 to the negative 5th, and c is negative 1.05 times 10 to the negative 7th. And then remember that the quadratic formula tells us that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, I'm going to cut this in half here. So let's plug in each of those values. Let's see if I can actually fit them in here. Let's see, so for 4ac, a is just 1, so I'm going to leave that out. And then we divide that all by 2. Okay, so if you want to pause and try to solve this for the values of x here, you can. I'm going to leave out the math here since we have limited space. So you should find that when we simplify this, we have negative 6.3 times 10 to the negative 5th plus or minus 0.000651 over 2. Now, one of those values will be negative, and remember that concentrations cannot be negative. We want a positive value for x. So that positive value is equal to 0.000294. And remember that that is equal to the concentration of hydroxide ions. Okay, so we finally found what x is. And it's never fun to use the quadratic formula. So if you have it programmed into your graphing calculator, that's great. If you don't, I'm sorry, I don't have it programmed into my calculator either, so I always have to do it the long way. All right, so now we can figure out the pH of our solution. Now, unfortunately, we have the concentration of hydroxide ions, not hydronium ions. So first we're going to calculate the pOH. So that will equal 3.53. Now remember that a small pOH value means we have a base. Now to find the pH value, we're going to use the fact that pH plus pOH is equal to 14. So we can take 14 and subtract the pOH value. And we get a pH of 10.47. And remember that a high value of pH means we have a base. So that makes sense. Okay, so that was a very long problem, but this is the method that chemists use to figure out the pH of a weak base solution. So it's good practice. Okay, so we're going to end the video there. This was a bit of a longer one, and we will continue our discussion in the next video.